Hi everyone, I'm just making a sort of review session video for the CBE40 final exam. Elyse and I have decided that we each wanted to do review videos, and so the way we decided to split it up is that this video will be all of the concept review, like definitions, what kinds of things it's reasonable for us to think you should know, what is a TXY diagram, etc. And then Elyse will post a video of practice problems. So I think if you're gonna watch all of both, I would probably watch this one first to sort of absorb the concepts, and then the video with Elyse you can kind of use to test yourself. So maybe, you know, after she explains the problem, pause it and think about it and then watch her solve it. And I think it makes sense to do that after you have sort of gotten as much review of the concepts as possible. That said, if you feel really good about the concepts and just want to watch practice problems, then this is not the video for you, and good luck. Before we start, I just want to ask everyone, please fill out your course evaluations. Both good feedback and bad feedback is really useful to us. I know I personally am thinking about going into teaching type careers, so any feedback you can give me that will help me be better, or be a good professor or be a good lecturer, because I'm planning on teaching more. I really want that feedback. And then also good feedback also helps us. We get teaching awards and everything like that. So whether you have good feedback or critical feedback or a mixture of both, please fill them out. They're really, truly useful to us. I read every single comment I get. Okay, so first, just some logistics about the final. We're gonna post it on B courses and we'll email you 10 p.m. Tuesday night Pacific time, and it will be due 10 p.m. Thursday night Pacific time. And then within that 48-hour window, you can pick any 3 hours that you want. We're not going to do any of the sort of, from the moment that we see you download it from B courses, you must submit it 3 hours later, because we know that some people will be trying to print the exam, some people have a lot of tech issues as far as like how long it takes you to scan it and get it uploaded, and we don't want any of those technological burdens like taking up any of your time. And I know some classes are doing exams where you have to be logged into B courses and B courses times you to 3 hours, but we also heard from a lot of you that internet access makes that hard. So we're gonna post a PDF of the exam, and then you are going to upload a PDF of your work. So that can be, we will leave as much space on the PDF as we would leave on a normal exam. So you can download that PDF and, you know, solve it on your iPad and like write on our PDF. You can print it and write on it, or, you know, I don't have a printer. The way that I would take this exam if I was in the class is that I would just look at the exam on my computer, and I would write out my work on like white paper and scan that. So that is a perfectly acceptable option. The one caution I would give you is like, please label your problems. If you're doing it that way, please label clearly like this work corresponds to problem 1, etc. And so that means that if we ask you any problem along the lines of like, label this diagram in some way, you're totally welcome to just draw the diagram on your paper and label it. So as long as it's clear, however you want to format that is fine. It's going to be open notes, open book, open any resources from this class. So that includes these discussion section videos, any Piazza posts that are already posted, but not like no Googling stuff, no contact with any of other humans, classmates or otherwise. We're going to leave the Piazza page open for any clarification questions. So like from the last exam, a lot of you asked, like, what does benign mean? So that question would be totally allowed. But what we're going to do, just so that, I don't know why anyone would do this, but if you tried to like post all of your solutions to problem 1, we're going to make it so all your posts have to be approved by us before they're visible to anyone else. So on timing and on everything else, please just, golden rule, treat others how you'd want to be treated. If you wouldn't want your classmates taking 12 hours on an exam you're taking 3 hours on, don't do that yourself, and hold yourself and your classmates accountable. We know that there are like Facebook chats and Discord and whatever else out there. Please just sort of hold each other accountable for using technology wisely. Some study or test taking tips. I would really recommend thinking ahead about what you think we will ask. For one thing, this is a great way for you to process what did I learn in this class? What information was important? What kinds of things do I think should be emphasized? But also, sometimes you can predict a problem and get it right. And that has happened to me. And it's really great if you predict the problem ahead of time, take a couple hours, solve it perfectly. And then when it's open note, you just sort of copy it all over. So that's something I do for every test I take. Even if I don't get extra credit for trying to write a practice problem, I do it anyway, just because I think it's a really great way for me to prepare. So I'd highly recommend that. I also recommend trying to explain the course material to someone else. Obviously before that 48-hour period has started, but that can be classmates. Obviously that's a little harder now that we're all working remotely, but highly encourage like group studies, Zoom chats. I think it happens a lot that something your classmate thinks is important you've totally forgotten about, and sharing that is useful, but also just the process of you explaining it, you learn a lot. So, try to teach your mom about TXY diagrams or whatever. Explain phase diagrams to your dog, like whatever works, but really think through how you would explain this to someone else, because really what you're doing on the exam is explaining it to us, making sure that you're explaining it right. Obviously the midterm and homework problems give you a good idea of what we have thought is important. And then when you're actually taking the exam, show what you know. Don't ever leave anything blank. We really try our best to give partial credit. So if you have written anything that is, relevant and correct and useful, you'll get some points for that. So even if you don't know how to solve it. Just try, write something. And similarly, like if you needed part A to solve part B and you couldn't solve part A, just say like, I assume my answer to part A is 50, and sort of show that you know how to solve part B. And then the last thing to think about is obviously when you're checking your work, read your answers from our perspective, and did you solve for X without telling us what X is? So making sure that we will be able to understand what you were trying to say. And sort of thinking, what knowledge is this question trying to test? Have I shown that I know that thing? Okay, so I'm gonna start with, I'm sort of gonna go chronologically throughout the material in the course. So starting with process flow diagram conventions. I'm gonna go quicker through the first half of the course because it's basically the same as our midterm review session. So I'm gonna go faster through that part and slower through the second half. And obviously, as always, please ask questions on Piazza, please email me, sort of whatever format works for you to ask questions. Obviously, Piazza is preferred if you think other people might share your question. So yeah. Okay, so process flow diagram conventions, I think we've kind of beaten to death, especially with the covered it in lecture and on homeworks and on quizzes. But the 5 sort of major things are that matter cannot be created or destroyed. So if you have, unless there's a reaction. If water is coming in, then water better be coming out, all of that stuff. Each unit should represent only one physical or chemical operation, so you can't have, I mean, obviously for like the Mars project, you could have a unit that's just like kitchen that is like doing all sorts of things, but for like a true process flow diagram, you should have like your mixer separate from your reactor, etc. Input streams need to be mixed, not simply combined. So we've talked a lot about mixers versus combiners. Basically, the only time combiners are allowed are if you have gases, if your two inlet streams are already the same thing, so like water plus water, or if those two streams are going to waste and there's no real need for them to be evenly mixed. Barring that, you should use a mixer. Stream compositions are preserved in a splitter. So that's just, you know, a splitter is a T-shaped pipe. So there's no separation happening that would cause your compositions to change. And then the last thing is more dense components should be shown below lighter or less dense components, leaving a separator. So unless the solid is ice, usually that means solid is below liquid. Then there's also our sort of more nitpicky things of keeping your lines perpendicular, how to deal with cross streams, etc. Okay, just some unit operations that by now you've seen a bunch that you should recognize. So a reactor is just a box with different stuff coming out than came in. We just talked about when you can use a mixer and when you can use a combiner. So I won't spend time on that. And then heat exchangers, we draw with the little squiggle in the middle. And then separators are sort of actually doing work of trying to separate A and B. This doesn't have to be pure B and pure A for this to be a separator, but we're changing the composition. We've done something to try to change the composition. And then splitters are the opposite of that. There's a T-shaped pipe where the same composition is coming in as is coming out. Okay, so for process design, some important concepts are residence time, so how long will each step take, and the reason that's useful, among other things, is sort of, if you could buy 2 of any unit that is used in this process, which one would you pick? And you should try to improve the one that has the longest residence time, because that's sort of our limiting factor for our process. And then, again, we've sort of talked about this a bunch, but always whenever you're doing process design, once you've designed a process that like works and accomplishes the technical goal, it's always worth going back through and adding heat exchangers and recycle streams to make your process more efficient. And then also just check the streams that are going into the whole process and out of the whole process. Make sure that there isn't a component that's coming in and also coming out, because that would just be inefficient. Okay, so moving into separations. By the way, process design around separations, like that last midterm problem is a really good practice for this. So I think if you got a really good score on that problem on the midterm, you should feel really good about this sort of section of the material. So the types of separation are phase-based separation, and often phase-based separation means you're changing temperature, not always, but often, in order to change the phase of one of your components. And if you are changing the temperature, you should list what temperature you're choosing to change it to. Then there's mechanical separation, so filters, sieves, centrifuge, that go based on size or density. And then affinity separations that are based on sort of some chemical property like solubility. So just sort of some drawings of how these might look. Flash drums you should now be more familiar with than you were when we first talked about this. That's a boiling point based separation where you have a liquid mixture coming in and then a gas and a liquid coming out. Distillation is also by boiling point. Distillation column is basically a whole bunch of flash drums stacked on top of each other, so it gets you a better, more complete separation. And the only other thing that's different is we take the gas stream that comes out of the top and we condense it, just sort of by convention. And then solubility, you might have a gas contaminated with SO2, so air contaminated with SO2 coming in and the air coming out, and some of that SO2 gets dissolved in the solvent, just as an example. And then you often, very, very often, have a liquid mixture, and you need to decide whether to heat it to get a liquid gas separation or cool it to get a solid liquid separation. And all else being equal, you should choose liquid gas. So it's a lot harder to cool than it is to heat. Cooling is a lot less efficient. Exception being if your mixture is sort of already at 200 C, then sort of letting it cool to room temperature doesn't take any energy at all. But if you're sort of already at room temperature and deciding between heating to 100 or cooling to -80, heating is more efficient. And then also solids are just annoying. They are goopy, they stick to stuff, you have to move them in some way, and liquids and gases are just, they can flow through pipes. And especially gases, I've said this a bunch, but like if you just have a container with a liquid and a gas in it and you poke a hole in the top, the gas leaves and you have done very little work to make that happen. Okay, I just want to again caveat this, that if you would have to heat 300 degrees to get a liquid gas separation or cool 5 degrees to get liquid solid, then you should pick liquid solid, but this is just sort of guidelines, all else being equal. And then just sort of before you randomly start just doing a whole sequence of assorted separations for no good reason, think about what your actual goals are. So if you have a mixture of A, B, and C and you want pure C, you know, maybe it's not worth just isolating A and then isolating B. If you could just isolate C, leave an A-B mixture that you throw away. So think about that, like efficiency-wise. And then also we tend to default to phase-based separations because we spend so much time on TXY diagrams and flash drums and all of that. But sometimes there's a very obvious answer that is, from one of the examples we did in discussion, if I grind up this pouch, there will be plastic, it will float. That is easy. So sort of look out for those obvious answers before defaulting to phase separations. And then is there a relevant chemical reaction or solubility? And then sort of like I was saying at the beginning, what order of separations makes sense? You know, maybe if I have A, B, and C and I want all of them to be pure, but I have 1 mole of A, 1 mole of B, and 500 moles of C, then if I get rid of my C first, all of my other units can be smaller than they needed to be before. So that can be something that influences what order you want to do your separations in. And then, you know, what data do you need? And in the context of an exam, what data do you have? So we will, you know, it is open book, but we will provide any physical properties you need. So we will provide the boiling points, the melting points, like anything, heat capacities, et cetera, anything you might need. So if you find yourself trying to find the table in the textbook that has the heat capacity of the things, maybe check and think about, that might be a hint that you don't need that and you're going down the wrong path. Okay. A lot of questions about flow and steady state. This is a slide that I've shown before. Really, steady state versus transient, all you need to remember is that if anything is changing with time, it's not steady state. So steady state just means, again, nothing is changing with time. So that sort of first question on the midterm, where you had the fermentation in the kombucha bottles, that was not steady state because there's a reaction happening and the bottle is sealed. So there's no way for that reaction to be happening at all while you're still at steady state. If you're producing a product and that product has nowhere to go, it must build up. So just sort of, whenever you're looking at a problem, just pause and think, will anything change over time, whether that's temperatures or amount of liquid in the system or compositions or anything like that. And, you know, this came up with the project as well. You tend to not have to think about startup and shutdown. So in the case of the reservoir, I don't really care, you know, in what year Shasta Reservoir was established and how many years of average rainfall it took for it to get full. I just sort of care about the community that's using this reservoir needs X gallons of water per year, and X amount comes in rainfall. It's really just the balance of in versus out, not sort of how long it took us. And so that's something that comes up a lot with recycle streams. People really want to say, I know what my initial input stream was. If I run that through my reactor, here's what my product stream is. But then you get tripped up because if you're recycling that, well, then now your input stream is different than it was before. And how do I deal with this? And the answer is, you just sort of, there's the first pass through the reactor, there's already stuff in the recycle stream. So you're already at steady state. Okay. These you should be very, very familiar with at this point, just some nomenclature on flow rates and composition. Flow rates are amount per time, and we call them like F1 would be the flow rate of stream 1, and the flow rate of component A in stream 1 would be FA1. Again, on exams, you can use different nomenclature if you want. Just be aware that I need to grade your exam and know what the heck you're talking about. So if you decide to call something X instead of FA1, somewhere tell me X is the flow rate of stream 1. And then composition is mole fraction or mass fraction, or percents if you want, if you multiply them by 100. So the mole fraction of A in stream 1 is the flow rate of A in stream 1 divided by the total flow rate of stream 1. And so if you just sort of rearrange that, you get the equation FA1, the flow rate of A in stream 1, equals the mole fraction of A in stream 1 times the flow rate of stream 1. And then the mole fractions in a stream have to add up to 1. Obviously, you can't have a stream that's half A, half B, and half C. That doesn't work. Okay, so mass balances, you should be able to recite this equation in your sleep, both for this class and for the rest of your career in chemical engineering or any kind of engineering. Accumulation equals in minus out plus generation minus consumption. If you are at steady state, and only if you're at steady state, accumulation is 0. So that was a mistake that people made a lot with the kombucha problem, is you're so used to everything being at steady state that you just crossed out accumulation sort of by default. And then in and out are flow rates, and generation and consumption are due to reaction. So if you have no reaction, you can cross out generation and consumption. And if you're at steady state, you can cross out accumulation, and then you'll get in minus out. But again, just be careful. A lot of people are so used to in equals out that they just sort of default write that when maybe there is accumulation or generation or consumption. But as on the midterm, you should be able to spit this out in 0 time. You should not need to look at your notes for this one. Okay, and then because we haven't really talked about this in a while, when to use mass versus moles. Mass is always conserved. Moles are not necessarily conserved. If there is no reaction at all, do whatever you want. Mass is conserved, moles are conserved. Mass of any given compound is conserved, so are moles. Everything is just easy. If there is a reaction, then total mass is always okay. And then moles or mass of elements, so hydrogen, carbon, are also okay. But mass of a species or moles of a species like H2O or CO2 are not okay. Unless you're going to sort of explicitly account for the generation and consumption terms. But you can't say H2O in equals H2O out if there's a combustion reaction happening, or any reaction that involves H2O. And then this came up on the midterm, but also comes up really anytime. If you are using stoichiometry at all, you need to convert to moles as you're doing that. So when you were trying to find the limiting reactant, and you know the stoichiometric coefficients, you need to convert to moles before those stoichiometric coefficients are useful. So if you have A plus 2B goes to C, you know you need twice as much B as A, but you need twice as much B as A in units of moles. Okay, and with mass balance problems that involve sort of multiple steps, the way that I always do it, and what works for me, but again, feel free to ignore this, is draw out your PFD if we haven't given it to you. Often on exams, we'll sort of give you the bones of a PFD just so you don't have to deal with that. Fill in any known information. I do that just because I want everything I need to know on my diagram and not in the sort of paragraph of text describing all of this. So I draw my PFD, read through the text once, and translate all of that onto the PFD, and then never look at the block of text again. Or if I'm checking my work, I'll read it again. But I don't want to have to keep sort of jumping back and referencing that. And then if there's any additional information, like a reactor conversion, or the flow rate of stream 3 is 5 times the flow rate of stream 2 or whatever, just writing that out in equation form. And then find a mass balance of any kind that has only one piece of information missing, meaning that I can solve it. So this is usually the hardest part, is sort of finding the first place to start. And I usually just sort of scan around, and usually, we're not going to give you a PFD that has 30 units and infinite balances, right? So there's only so many balances there are, and just sort of think about what you're looking for and just sort of scan around and try to find a balance that will be useful for that. So that can be a total mass balance over the overall system if you happen to know the total flow rates of all but one of the streams, a component balance over the overall system, or some subsection of the system. If you know a lot about the first separator, start there, whatever works. And then just sort of, now you have one more piece of information, where does that lead you? And you just sort of follow that. And just be a little careful, because a lot of times you don't need to fully specify every stream in the system in order to get what we have asked for. So sort of after a couple balances, pause and say, am I moving in a direction that's useful to get me to the one thing they asked me to solve for? And then this was also tested on the midterm. So the conversion of A, we call capital XA, and that's what fraction of A that entered has been converted into something else, anything else. And so, I guess this final is open note, so the don't memorize anything mantra is less relevant, but you also shouldn't need to look at your notes for this one. That's the conversion is just how much was converted divided by how much came in. And how much was converted is how much is no longer there in our outlet stream. So that's in minus out, divided by in is how much came in. And then be comfortable with the difference between reactor conversion, which is just the conversion on the specific subsystem that is just the reactor, versus the overall conversion, which is the conversion in your system as a whole. And if the reaction you're looking at is the one that's sort of the whole purpose of the system is to make B or whatever, your overall conversion should be higher than your reactor conversion. That's sort of the whole point of having a recycle stream or anything more than one reactor. Limiting reactant is which of your reactants will run out first. So there's a lot of ways of solving for this. The one that I always use is I convert everything to moles. I pick a reactant and I say, in order to fully consume A, how much B do I need? If I have more B than I would need, then A is limiting. If I don't have enough B to use up all my A, then B is limiting. But I think, a lot of you did it a little differently on the midterm and got it right, and that's great. Whatever works for you. And then the last thing is percent excess. And this one is tough. It's how much extra do we have relative to what we would need to achieve 100% conversion of the limiting reactant. So F out is not ever in this equation. So it's FA in divided by FA needed. So this is what's in the numerator here is how much we will never ever need, even if we had perfect conversion, divided by how much we would need. So that one you might have to look at your notes for, just because there's a lot of ways that make intuitive sense of thinking about percent excess. Okay, so that so far is what was relevant up to the midterm. And then everything I'll talk about from here on out is the stuff we've learned after the midterm. So now would be the time to pause and get water or whatever. Okay. So just going through in order of what discussion sections we did. Discussion section 7, which is the one right after the midterm, was on Excel and how to use Excel. You don't need that for the exam. We're not gonna ask you to use Excel if you don't have Excel on your laptop at home. That's fine. And in fact, please don't try to solve a problem in Excel on the midterm. It is very hard to actually show us step by step your work. And so if your final answers in Excel are wrong, it's really hard for us to figure out what went wrong. So you would be hurting yourself. And we won't ask you any problems that are like, solve this problem 5 times with 5 different inputs, which are the kind of problems that Excel is really useful for, so that you can just sort of change one number and everything changes. We won't ask you a problem like that. So put the Excel away. That said, that week we did discuss some sanity checks, which are sort of once you've built your spreadsheet in Excel, or when you've solved a problem without Excel, it's always a good idea to check sort of, does the answer I got make sense? Is my conversion over 100%? That's probably wrong. Is a flow rate negative? Provided that flow rate is mass, that's probably wrong. If it's energy, I guess you could have the energy flowing in. But like with energy, you should be able to think about, does the sign of this make sense to what I thought it was going to be? And then, is your answer the right order of magnitude? Did you get a flow rate of 10 million when you had a flow rate in of 10? So just think about whether your answer makes sense. That said, there are, it sometimes happens that, your flow rate in is 100 kilograms a minute and your recycle stream is 10,000 kilograms a minute, and people sort of panic. And that is not necessarily something to be alarmed about. Recycle streams often have really, really high flow rates, and that does not mean you were wrong. So then after that, we moved into economics, and we had a homework on this, so you should have a lot of practice problems available. So just the basic definitions. Revenue is just how much money comes in every year. So often that's, because we're often doing chemical plants that are making products, how many kilograms are sold per year times how many dollars do we get per kilogram. But, that revenue can come from all sorts of things, depending on what process you're looking at. And then depreciation is also in units of dollars per year, and you calculate that based on just total capital costs divided by equipment lifetime. So those capital costs are one-time expenses like buying your plant, buying your giant reactor, the installation costs of installing those reactors, etc. They're things that happen once. And then your operating costs are your total costs. So that includes depreciation, which you just calculated, but then also includes your annual expenses, like how much you have to pay your employees, how much you have to pay for sort of regular maintenance, A big one is the materials, so your reactants in your product. And then again, also the depreciation. So your operating costs includes the depreciation that you just calculated. So your profit in dollars per year is your revenue minus your operating costs. So your revenue you calculated up here and the operating costs just calculated. And then ROI, which is return on investment, is in percent per year. So it's your annual profit divided by your initial total capital cost. And I think this, some of you discovered the hard way. ROI is defined 10 different ways in 10 different fields. So the econ definition of ROI isn't the same as the engineering definition of ROI. So write this one down also. And then one that comes up a little less often is that particularly with reactors, the cost of the reactor does not scale linearly with the amount of volume. And that's because you're not paying for the empty space in the middle of the reactor, you're paying for, you know, the fancy titanium sheeting that the reactor is made of. So you're paying for the surface area. So if we gave you some constant, we would have to give you this constant. The cost of A scales to the power of 0.6 with the volume. So if we gave you a 1 liter reactor costs $10, how much does a 100 liter reactor cost? You would use this equation to figure it out. And then when this came up on the homework a lot, when you are evaluating which choice you want to make, you have two possible processes. Which one do you want to use? ROI is the relevant thing. So just because you have twice as much profit, you know, maybe you have 5 times as much expenses, and that's actually a worse deal for you. So if we ask you which of these two things is better, calculate the ROI. And then whichever one has a higher ROI, that's the process you want. Okay, so then we moved into energy balances. So there's a lot with energy balances, and I'm sure Elyse will do some practice problems. But what I want to emphasize is this sort of usual equation of accumulation equals in minus out plus generation minus consumption applies to everything ever at all times. But with energy, energy can't be created or destroyed, so generation and consumption are not relevant. Energy, as you all have heard a million times, I'm sure, cannot be generated or consumed, it can just change forms. So accumulation is in minus out. And then often in energy situations, not always obviously, accumulation is not zero. So if we ask you to solve a problem where, you know, I take a pot of water and I put it on the stove and I'm heating it, that water is obviously accumulating energy as it heats up. So one, you know, practice problem if you want to test yourself is if I put 1 liter of room temperature water on the stove, how much energy have I put into it by the time it has all boiled? And the way you would do that is figure out how much energy it takes to heat the water to its boiling point, and then how much energy does it take to boil off all the water. Another way of looking at energy is that the change in internal energy, which is delta U, equals Q plus W, where Q is heat into the system and W is work done on the system. And this is one, as Dr. Siston talked about, that a lot of people have a lot of disagreements about the sign on this, including within chemical engineering. There are 2 like very famous textbooks that are very commonly used that have different conventions. So this is the convention that I like, because everything that's going into the system and adding energy to the system is positive. But some people really think that it should be Q minus W, and W should be defined as work done by the system. And that is fine. But just be careful and be clear. So like I was talking about with the boiling water example, our most common sources of energy change are a change in temperature or a change in phase. You could also have a change in, potential energy if you throw the pot of water out the window, but that is typically less relevant to our engineering concepts. So for changes in temperature, we use MCP delta T, and just to be complete, what we're actually doing is calculating the change in M times CP times T. But we typically assume that CP is constant. And if we give you, here's the CP of liquid water, then you should assume that it's constant. That is a valid assumption. Because if we didn't, you'd have to plug in that formula for CP and integrate over temperature, and we're not gonna make you do integrals. You will have to next year, but that's a later problem. And then you should set it up so that M is not changing. So you should take, if I told you to solve it where all of your water heats up, but only half of it vaporizes, then, M for the heating part of your process should be your 1 liter, and then define M differently for how much actually vaporizes. So when we do that, we end up with M is constant, CP is constant, and T is the only thing that's changing. So we get MCP delta T. And just be careful, because this came up a lot on the project. People took ice at -40 to water at 20 and just did MCP delta T with a delta T of 60. But in that case, you haven't accounted for the energy that it takes to actually melt your water. So what you should do is heat ice from -40 to 0 with your solid ice heat capacity. Then find the energy change to change the phase, so using your delta H, and then heat your liquid water with your liquid phase heat capacity from 0 degrees Celsius to 20. And so these delta H's of phase change, the delta H's of melting and vaporization are positive. Again, I know this is open note, but the way that I remember that is twofold. One, when we sweat, the reason that we do sweat is that the water on our skin absorbs energy, absorbs heat from us as it vaporizes. So if it was releasing heat, then we would get hotter when we sweat, and that would be bad. And then the other way I think about it is that the molecules in a gas are just moving around a lot faster. They must have more energy, so they must have absorbed energy, and so their delta H would be positive. And then if we give you delta H of melting, then delta H of fusion is just -1 times that. And similarly with condensation, is -1 times the heat of vaporization. And then some definitions that are relevant for phases. Our partial pressure, PI, where I is our component, so A, B, water, whatever, equals XI, so the mole fraction of I times the total pressure, P. And then specific quantities are those quantities sort of divided by amount. So specific volume is volume per mass and is the inverse of density, and we would draw that with a little bar on top. So that comes up sometimes with, well, first of all, PV diagrams. The V is specific volume on the bottom, but then also another way of writing the ideal gas law is PV equals nRT. If you divide the N over to the other side, you have V over N, and that is specific volume. So you might write P times V bar equals RT. Okay, so phase diagrams. PT diagrams are sort of the easier ones that people are more comfortable with typically. So a typical material is shown on the left here, where at very high pressure and low temperature, you have solid. At very high temperature and low pressure, you have gas, and then the middle thing is liquid. And the point here where all three phases coexist is called the triple point. And then if you are using this diagram for a mixture, then the P, the pressure axis, is the partial pressure of that pure component. And one thing that comes up a lot is people get confused because they know that phase equilibria exist. And so TXY diagrams exist where there's this whole region of liquid vapor equilibrium. But what you should remember is that these are single component phase diagrams. So you're looking at pure water, and pure water at 1 atmosphere has a sort of immediate phase transition at 100 C. And that's very different from water when there's air around, in which case there is a wide region of phase coexistence. And just sort of recognize that because water is weird and the solid is less dense than the liquid, this solid-liquid coexistence line is tilted the wrong way, relative to what we'd expect for a normal mixture. So we should be able to give you a PT diagram and say, is this water or not? Okay. PV diagrams are a little more confusing for people typically. And so you should be able to label all the regions on a PV diagram and justify how you know which region is which. So the way that I think about it is, I know that the biggest thing with the biggest volume is always going to be vapor. Gases are much bigger than liquids or solids at the same pressure and temperature. One thing to note is that PT diagrams are at constant volume and PV diagrams are at constant temperature. Okay, so our biggest thing is vapor. And then also typically our smallest thing is solid. So PV diagrams of water look a little weird because the volume of the solid can be sort of, that region can look weird. But for a typical substance, the smallest volume thing is going to be a solid. And then we know that there must be solid vapor coexistence somewhere, and the only region that touches both solid and vapor is the solid vapor, is like this region down here, so that one must be solid vapor. And then similarly, solid has to touch liquid somewhere, and the only other region that's touching solid is this one right here, so that has to be solid liquid. And then obviously the solid liquid region must touch the liquid region, so this one has to be liquid, and then our last one has to be liquid vapor. So that's how I remember it. That's not to say that there are no other valid explanations. And then the critical point, which is sort of where liquid and vapor become indistinguishable, is this point right here, above which sort of liquid and vapor stop making sense. Okay, oh yeah, and then the triple line is anywhere that touches all three phases. So in this region, we've got solid, liquid, and solid vapor, so we've got all three. And then over here, we have liquid vapor and solid vapor, so we have all three. So what was a point on our PT diagram is now a line on our PV diagram. Then we also talked about degrees of freedom. So that is the number of variables to fully specify a system. So we should be able to say on this PT diagram, find a point with 2 degrees of freedom, find a point with 1 degree of freedom, etc. So the rule that we use for that is called the Gibbs phase rule. And that is the degrees of freedom, DOF, equals 2 plus C minus P. And, you know, people always want to memorize this one and again, always get it wrong. So the way I remember it is I know that the triple point is a point on my PT diagram. And so it must have 0 degrees of freedom. So if I plug in to what I think is the equation, 1 for for components, so it's a one component system, and 3 for phases, because it's the triple point. It has solid, liquid, and gas. I should get 0 degrees of freedom. So that's a way for you to just check. 2 plus 1 minus 3, yes, that's 0. Okay, I have the form of this equation correct. And then we talked about Raoult's law a little bit towards the end. So Raoult's law applies to ideal mixtures, and the equation is just the partial pressure of I equals the saturation vapor pressure of component I, so we call that Pi star, times the mole fraction of component I. So the definition of saturation is just the maximum concentration a component can reach in a mixture. So we often think about water vapor in air, and at the point that it reaches its saturation concentration, we will get rain or fog, or in some way the water, there can't be that much water in the air and some of it will start to condense out. Partial pressure, we've talked about a lot. It's the partial pressure of I or X or A or whatever component you have divided by the total pressure. And that will equal the partial volume or the molar concentration. And then the equilibrium vapor pressure is the pressure exerted by vapor in equilibrium with its liquid phase. And we often apply all of this to water to get humidity. So humidity is just the partial pressure of water in air. And that's not so useful because how humid that will feel to us depends on how hot it is. So we often talk about relative humidity. So the humidity today is 80% or whatever it is. And we define that as the actual partial pressure of water divided by the saturation partial pressure of water times 100%, just to convert it from a fraction to a percentage. So if it's 99% humidity, that means with, just a little more water, we will get fog or rain. Okay. So the last major thing we talked about was flash drums. So the very basic picture of a flash drum is we have a mixture of A and B coming in at some flow rate with some composition of A. We enter a flash drum, and then we have some of our, I made the same mistake again. This stream 3 is liquid. So we have a liquid stream coming out and a vapor stream coming out. So the vapor stream will be concentrated in the more volatile component, and the liquid stream will be concentrated in the less volatile component. So again, sorry, there should be a vapor stream and a liquid stream. And so the way that we analyze these systems is using TXY and PXY diagrams. So first, with a TXY diagram, what we're showing on the left is temperature. If we're using a TXY diagram, then we must be at constant pressure. And then what we're showing along the bottom is X, M, and Y, M, where we have a mixture of M and something else. So over here, we have pure M. And if we go along here, we can find the boiling point of M. And then over here, we have no M, so we have pure, I think it's K is the other component. And so we can find the boiling point of pure K. And in this case, the boiling point of M is lower than the boiling point of K, and so M is more volatile. We can also label the phases, and we know that at high temperature we have vapor, so this up here would be the vapor phase, down here would be the liquid phase, and this region in the middle is our liquid vapor equilibrium region. And then our PXY diagram is exactly the same. In concept, we're at constant temperature, this axis is pressure, but now our components are going to be flipped. So at high pressure, we favor the liquid phase, and at low pressure, we favor the vapor phase. So for our TXY diagram, this was vapor, the sort of upper region. And for our PXY diagram, this is our liquid phase. So the way that we analyze these is if we have some feed composition, we call it, let's say, ZM, and let's say our input composition is 0.4, and I tell you we're going to heat it to 70 degrees C. We go up and we have 70 degrees C right here. And like I said earlier, this is the vapor phase and this is the liquid phase. So we can draw our tie line and find our vapor composition over here and our liquid composition over here. So we now already know we have two streams leaving our flash drum, one vapor and one liquid, and we already know the composition. And then what we use to find the how much stuff is in the vapor versus the liquid is what's called the lever rule. You guys have used this on your homework. And basically what we find is the fraction of the feed that becomes vapor is the length of the liquid arm divided by the total length of the tie line. And I've talked about this before, but the way that I remember that is that if I have my liquid mixture, I heat it up just above the bubble point, I'm gonna have one bubble, very small bubble of vapor. And my liquid composition is gonna be pretty close to my inlet composition because I only have some small bubble. So why would the liquid composition change very much when I haven't removed that much stuff from it at all? So the length of the liquid arm is going to be really short because the liquid composition is really close to the feed composition. And so our fraction of vapor should be small because it's a small bubble. So you want to divide sort of the small part of the tie line divided by the total length. So in this case, if I wanted the fraction that becomes vapor, I would take the length of the liquid arm, which is the part of the tie line touching the liquid, divided by the total length of the tie line, and that's what fraction of stuff in the feed will become vapor. Okay, so that is all of the sort of actual material that we covered this year. Like I said, I'm sort of just going through these again. You'll have some practice problems, and one thing I would really think about is ways that we can combine these concepts. So we've done a lot of phase diagrams and also a lot of mass balances. Could we ask you to read something off of a phase diagram and then use that in your PFD to solve for some mass flow rate? Can we combine energy balances and phase diagrams? So just sort of when you're writing practice problems, that's something I would think about is how can these different concepts we've taught you, how can I combine them? So I'd really, really recommend doing that, the sort of exercise of writing a practice problem or a bunch. It's really useful. And we'll also send out all of the practice problems your classmates wrote. And I would recommend definitely taking the time to read those. So yeah, plan ahead for what you think we'll ask. Trying to explain the material to someone else really helps you learn it better. Checking through the midterm and the homework problems. And then as you're actually taking the test, just make sure you show us what you know. Don't leave anything blank, just sort of, if you can in any way show us that, like, I can tell you're trying to test me on TXY diagrams and here's what I know, that lets us give you some points. And then just make sure that the answers you're writing are clear to us. We really want to give you partial credit and want to help you out here. One other thing I wanted to say is there will be a couple of people taking it early and none that we know of right now, but it's possible that there will be people taking it late. People are getting quarantined for various amount of time in various countries. So please, please don't talk about the exam with your classmates when you don't know whether they've taken it or not. Don't sort of as soon as you're done, post on Piazza, how was I supposed to solve problem 2 or anything like that. Okay, good luck studying. Please ask us questions. And I hope everyone is safe and doing well and staying healthy. And please let us know if you need anything or we can help with anything. Okay, that is all.